Okay, folks, so welcome back. Wonderful good morning, good afternoon, good evening, again, whichever part of the world we are connecting in today. And this is um, the Mysteries of the Universe Institute Lecture Series at the Indian Institute of Technology, Roorkee in India. And today we are delighted and so privileged to have Professor Cumrun Vafa, the Hollis Professor of Mathematics and Natural Philosophy at Harvard, with us as our distinguished speaker. And he he did his PhD under the supervision of Professor Ed Witten, our previous speaker. Professor Vafa's research is focused on the nature of quantum gravity and the relation between geometry and quantum field theories, which he has made so popular and is referred to as geometric engineering of QFTs, quantum field theories. He's globally known for his work on topological strings, mirror symmetry. Maybe some of us have that real fat book on mirror symmetry. The beautiful, it's a very thick book, both from the perspectives of physicists and mathematicians. And of course, he's the father of F theory, and he's contributed so much to F theory phenomenology. And in more recent times, he is known for what are now referred to as the swampland conjectures. He has a very long list of awards and honors, and it'll take probably, I don't know how much to even begin to go through them, but I would mention the following: that he is the recipient of the Breakthrough Prize in Fundamental Physics for Advancement of String Theory in 2017. He was a recipient of the Breakthrough Prize in Physics Frontiers, the Physics Frontiers Prize in 2014. He is the recipient of the Dirac Medal in 2018, given by the International Center for Theoretical Physics, Trieste, Italy. He got the Danny Heinemann Prize for Mathematical Physics in 2016. He became the member of the American Academy of Arts and Sciences in 2005. He became a member of the National Academy of Sciences in 2009. So before we request Professor Vafa to kindly deliver his lecture, just two little things I want to point out. A, probably we are already aware of this. This is going to be a slightly different kind of a lecture than the ones that we've had thus far, because this time it's going to be an interactive session between our speaker and the non-speakers, the rest of us. And so I think it's going to be really great fun to experience this. And the other thing is that all the participants, all the attendees are requested to kindly fill in a survey, which is going to be floated by our incredible team of Physics and Astronomy Club that I refer to as Packers. So they're going to be, I think, posting, if I'm not mistaken, on the chat a short survey. You are all humbly requested to please do take some time out to fill that survey. So I think that's pretty much all that I wanted to say, and I would very humbly request Professor Vafa to please deliver your lecture. Professor Vafa.
Thank you very much, Alok, for inviting me to give this lecture, and it's a pleasure to be back. I think it was, I don't know, it was about a few years ago where I gave a talk again virtually here. So it's a pleasure to be back here. Let me share my screen. I'm assuming you can now see my screen.
Yes.
So great. So let me put the slides on. So I'm going to talk about puzzles and its relation to the physics, to the universe. It's based on a book that I just put out, Puzzles to Unravel the Universe. And this book is based on internal freshman seminar that I've been teaching at Harvard in the past 9 years or so. And it's basically tries to give introduction to physics and principles using fun math puzzles. And it's not supposed to be too complicated. It's supposed to be simple puzzles. It's not like you don't need too much math background, but the idea is that you can get to many deep facts about physics just by using some fun puzzles. So So with that in mind, I first of all apologize to all the experts in the audience, which I'm sure there are many. So I'm gearing this towards people who are not necessarily as familiar with either math or physics, and they are people who are trying to kind of get interested in it. So I think that's the perspective I'm taking. So for the physics and math experts in the audience, which are, I'm sure the majority you are, this could be viewed as a kind of an introduction for others who you might want to present the subject to, perhaps. Anyhow, so that's the motivation for the talk. And so just let me start by reminding and reviewing the connection between math and physics, which have a beautiful interaction through over many millennia. Some highlights from the past. I guess we can start perhaps with the Greek mathematicians and philosophers. And math and geometry had a very strong link in their mind. They were trying to explain how things work based on beautiful mathematics. Platonic solids, their symmetries were representing what they thought were the 5 basic ingredients in the universe. For example, they appreciated symmetries, and they were trying to kind of connect it to the universe as they saw around them. And is followed by other cultures and other civilizations, among them, of course, the Indians. Indian mathematicians played a key role. Islamic scientists continued these traditions. For example, they continued with the measurements of the radius of the Earth using simple geometric facts, which were beginning to apply concepts of mathematics to more concrete things in the universe. For example, measurement of the height of the atmosphere in the 11th century, just by basically simple geometry of the sun hitting the upper atmospheres, upper edges of the atmosphere after the sun has set down, and how long does it take before the last ray hits the upper atmosphere, was used to measure the height of the atmosphere. So these are very simple ideas, and math was beginning to be used in trying to get an insight about where we live and how the universe around us looks. This tradition continued with more developments in other places. In particular, Newton, as an example, did a major advancement of all these ideas by using and developing, actually, calculus, and used that to describe the laws of mechanics. And later, Gauss, again, tried to use geometry to understand better aspects of our universe, and understanding aspects of it having to do with non-Euclidean geometry came to fore. For example, if you go to top of 3 mountains, and if you look at the light rays coming from the top of each of the other 2 mountains, do the angles that you see between these light rays, do they add up to 180 degrees or not? And these are the kind of questions that became natural to ask. Maxwell, in studying electricity and magnetism, captured beautiful equation, captured by beautiful differential equations, which described how the electricity and magnetism work, and in particular, how the electromagnetic wave is a description of light. Riemann, mathematician, talked about geometry and Riemannian geometry, and how, in fact, he thought about how he can possibly unify electricity and magnetism with gravity. He was trying to do something along the lines that actually was later successful due to Einstein. And Einstein's geometric description of gravitational forces is a remarkable connection between physics and mathematics. It basically geometrizes gravity by saying that the curvature of space around us is, which is the left-hand side of his equation, is related to the matter that is there, and that's the right-hand side of the equation. In other words, the response of the space-time fabric to the matter, the geometric aspect of gravity. And then further ideas, Kaluza and Klein tried to extend Einstein's theory to more than 3 + 1 dimension, to 4 + 1 dimension when you have 1 extra spatial directions. And again, these kind of ideas led to some simple models where gravity and electromagnetism could be unified. So my area of research is string theory, and the aim of string theory is to unify fundamental forces and particles into one framework. And it aims to describe physics from the tiniest scale to the biggest, which is the whole size of the universe. And basic postulate is that the fundamental particles are replaced by strings. And in particular, we think about, for example, quarks, the 3 quarks that make up a proton, themselves as being made of objects which are extended like strings. And it resolves, the string theory resolves the inconsistency between quantum gravity and quantum theory and gravity. In other words, if you did not have strings describing basic entities, it turns out that gravity will be inconsistent with quantum theory. So string theory provides a resolution of this conundrum. And the interaction between them is quite geometric. You see 2 strings coming together, and they interact in that way and join to become 1 string, or the opposite process where the 1 string decomposes to 2 strings. It's purely geometric, and this is what we call the pairs of pants diagram, because you can see a pair of pants as capturing this interaction as it moves in time. Now, this area of physics is very mathematical, and it involves many abstract ideas. To begin with, the dimension of space is more than 3 + 1. It's 9 + 1. We have 6 dimensions, which are tiny, that we don't see in our universe. Now, strings wrapped around these tiny dimensions lead to insights about how black holes work, for example, and how the beginning of the universe looks like, etc. So these extra dimensions turn out to be for good use and not just tiny for no reason. And so we can think about the macroscopic space as like this extended plane here I've depicted in this figure. And the internal spaces could be viewed as these tiny little spheres which are at every point in the space. And we demand that these extra dimensions to be curled up into tiny compact spaces so it avoids any contradiction with observations. Now, my aim in this talk is not to go to these abstract ideas so much, but actually to see whether or not we can illustrate some of the simple ideas by basic principles of puzzles. Namely, the vantage point of simple puzzles may give us a deeper understanding in some cases of what these principles actually mean. And moreover, it's fun. It's fun to deal with puzzles and try to solve them and try to see what's the meaning of these puzzles and is there a deeper meaning. And here I give you some examples, by no means complete, but just a few examples that can show how some of these principles in physics can be illustrated by fun puzzles. In the book, there's of course many more than the one I'm going to be showing here. So let me start with a simple topic, which is very dear to the heart of physicists, the symmetry and conservation laws. And so I start this by illustrating with the following puzzle. Suppose you have 2 containers, a green container and a white container, and you take a cup and you fill it with the green paint and you pour it into the white paint container, and then you stir it, and then you do the same thing, but now you take it back from the green from this mixed container, the same amount. I think this didn't work, so let's go back. Let's try it again. So let's just see if it works here. So again, let's do it again. So again, the green container, we take a cup from the green container and I pour it in the white container. And then we do the opposite by taking the same thing from the mixture. And then put it back into the green container, the same amount. And then we again mix it. Okay, and then we put the cup down. And then we ask the following question. We ask, which container, the green or the white, which container has the highest concentration of the other color? So that's the question we want to address. And I think if we can do this via chat, that would be fantastic. So I just want to get your take on it. Let me see if I can arrange that. Let's see. I will pose a chat. Those who think have a green has the more of. Oops. Those who think, let me just go back here. Those who think that the green has more of the constant, more white in it, write G. Those who think white have more green in it put white, and those who have W, I mean, and those who think they are equal put E. So G, W, and E, so we can respond. I'm just curious to know what you guys think. Okay, so we have a lot of E's, W's, and some G's. Okay, okay. So overwhelming number of you say E, which is actually the correct number. It's equal amount of concentration between these, and the reason for it is basically the symmetry principle. And you see, originally, in fact, the most people answer typically. This is a physics audience, so I guess it's hard to get the typical answer because you know better in some sense. The most typical answer is that the white has more green in it. And the reason is that when you pour the green into white, it was pure green. And then when you took back from this mixed container, when you took paint back to the other one, it was only from the mixture. So it wasn't pure white anymore, it was mixture. And therefore, you would think that the white has more green than the green has white. And that is not the case. And to deconfuse oneself, one thinks about the symmetry. And the symmetry in this case is that you started with equal amount of green and white. And then at the end, when you take one cup from one to the other and put that back, the total volume at the end is also equal between the two containers. And now you ask, in the green container, the amount of white that was missing, where is it? The amount of green that's missing, where is it? Well, it should be in white. And that same portion of that white must be missing and be back in green. So therefore, they are equal in concentration. And so that is, you can think about this as unmixing them, and then the white and green have been exchanged in place, and you can put them back in their original places. And then, of course, you will see that they had to be equal concentration in that way. And so that's just a simple idea about the conservation and symmetries. You can also see that by a deck of cards, if you have 10 red and 10 black cards, and if you take 3 of the red and put it in the black cards, and you mix you shuffle the black cards and take 3 cards back from this mixture and put it back in the red cards, and then mix them and also shuffle them again and ask how much mixture do you have? Do you have more red and black or black and red? Of course, that's the same. And it's related to simple idea that the total number of cards is 10, and whatever is missing from one pile is in the other group, and so forth. So therefore, it does not change that number. So just see if we could see that back again. Let me didn't just go back here. For some reason, this is okay. Good. So let's just see if we can see how that goes back here. Yeah, so in other words, you see that in this pile, you have 2 black cards and in the red pile and 2 red cards in the black pile. And of course, that's the total number is 10 on both piles. So whatever is missing from red is in black. And that's the easy way to see that they had to be equal. Okay. Now, Aristotle thought heavier objects fall faster. And, this is a very common perception. So I think everybody would think, yeah, of course, heavier objects will fall faster than lighter objects. And this question is kind of, in some sense, intuitively obvious, but wrong. And Galileo argued that, no, in fact, all objects fall at the same rate. How did he argue this? Well, he did experiments. He convinced himself by experiments that heavier and lighter objects fall at the same rate. But believe it or not, at that time, experiment was not the key driver of science. So people asked him, what is the reason? How would it be that it had to be like this? It doesn't make any sense. So he had to come up, in addition to experiments, with a theoretical explanation of why this is not so strange. So how did he do that? Well, he said the following. He said, imagine having 3 identical bricks of the same size and drop them from the same height. Of course, they will fall at the same time. That's kind of obvious. Okay, so everybody says, yes, we know that. That's kind of trivial. By symmetry, by the fact that they're from the same height and the same shape, same size, sure. So then he says, okay, what if we move some of the bricks horizontally in the same height and then drop them? Well, of course, again, they fall at the same rate. It's kind of clear. Because of symmetry, it doesn't matter whether they're close to each other or not. It's just the fact that they're starting from the same height. So then he said, okay, what if we actually go get two of them so close that they're actually touching each other? What happens then? Same thing, should fall at the same rate. But then he said, this is twice, the two bricks together is twice as big as the one brick, and you kind of agreed that it should fall at the same time, and it kind of makes it intuitive. Again, here, he's using symmetries. The fact that the symmetry in this case is horizontal translational symmetry does not affect the outcome, and therefore convinces you by this symmetry argument that two bricks touching each other should fall at the same rate by this symmetry. Again, the simple idea, but deconfuses a rather confusing point. So symmetries are fun, but even more fun is spontaneous symmetry breaking. So breaking of the symmetry is the more fun phenomena. So let's give an illustration of it by using a simple puzzle. Suppose you have 4 towns, A, B, C, and D, and you're instructed to find the shortest highway system which connects all 4 cities. The highway system should connect every city to every other city, but it doesn't have to be a direct highway system from each city to another. As long as you can get from any city to any other city, you're fine. And you just want to make the total length of the highway minimal so as to minimize the cost of the construction. So the question is, what is the best highway system? How many think this is the answer? Put yes or no in the chat. Okay, so a lot of you say no, and some of you say yes. And the reason that yes might have looked natural is that it is nicely, it's a nice symmetric structure, but there are other symmetric structure. How about this one? How many think this is the configuration? Please put yes or no in your chat. Okay, so majority think this is no. And indeed, you might think that if it's kind of like this, you might as well remove one of the edges, because you can get from the other ones, from one to the other by even removing one of the edges. For example, if you remove the highway CD, you're still going back to the same total. You can connect everybody, but you have a shorter highway length. And you can then ask, well, what if you move the AB highway parallel to itself? It doesn't matter where you put it. And you can, for example, put it down here. It would be still the same total length. And it turns out that even this is not the right answer. And it turns out this is the right answer. The right answer is that you have to bend it inwards, the highway, by 120-degree angle, so that these 3 angles that they make is each 120 degrees. And this shape turns out to be the minimal total length for the highway. Now, why does this sound strange? The reason this sounds strange is that even though A, B, C, and D are on the corner of a square, the resulting highway does not respect all the symmetries of the square. In particular, if you want to get from the city A to city B versus from city A to city C, clearly the distance from city A to city C, which geometric distance is the same, but the highway distance is shorter, namely from getting from A to C is faster than from getting from A to B. In other words, the highway system has broken the symmetry of the square, and that's just because you want to find the total length to be shorter. So that's an example of this, an unintuitive way that the symmetry breaking comes in. In fact, there are older examples, and the early Greek philosophers already had thought about these notions of symmetry. They had already understood that Earth is round, and they thought it was at the center of the universe, and they thought it's not moving. They thought it's not moving because if you look at the night sky, except for the spinning around the axis, they noticed that during the seasons, the stars are relatively in the same position, so therefore they kind of assumed that everybody is stationary with respect to Earth, and therefore Earth is stationary itself. So Earth is not moving, and they wanted to have an explanation of this fact. And they tried to use symmetry to explain this fact. So they said, look, Earth is at the center of the universe, and the reason it's not moving is because if it were to move, it has to pick a direction and to go in that direction. But picking a direction is not allowed, because by doing so, you're breaking the spherical symmetry. The fact that you have picked a direction breaks symmetry, and therefore symmetry breaking is not allowed. You start with a symmetric situation and you have to have a symmetric answer. And that's why it's not moving. Okay, so that was their use of symmetry to try to explain why the Earth is stationary. And Aristotle said this is not a good argument. And the way he argued was that, well, this is a version of the way he argued was, suppose you have a person, you put a person at the center of a circle, and you put loaves of bread on a circle whose center is that person. Now, the question is, what happens next? Well, he said that person is not going to stay there. It's going to go out and get the food. I know that it breaks the symmetry, he said, but it doesn't matter because the person is not just going to sit in the center of the circle when the food is around them, even though that they are equally distributed in a circle around him. He doesn't care that he has to pick a direction to break the circular symmetry in doing so. He will do that because that's the optimal situation for him. He wants to get food. In other words, broken symmetry is sometimes more optimal and more preferred to preserving the symmetry that you start with. And this was the point that Aristotle already noticed and said that therefore this is not a good explanation of why the Earth is not moving. Maybe it would have been preferred for it to be moving. In other words, he argued that spontaneous symmetry breaking might have had to play a role. So therefore he didn't accept the argument that the Earth is not moving. And in fact, spontaneous symmetry breaking is in fact imprinted on our bodies. We live in a, by and large, horizontally symmetric situation where if you look at around 360 degrees around us, it's more or less symmetric. And therefore, you would have thought that evolution would have made our body 360-degree rotationally symmetric, horizontally symmetric, but that's not the case. Just imagine if it was 360-degree symmetric, our eyes would be all around, and that's not the case. So spontaneous symmetry breaking is imprinted on our bodies. Why is it that the nature decided to have the eyes in the front and not all around to make it symmetric? So it has broken this rotation symmetry just to a reflection symmetry, approximate reflection symmetry in this case. Why did it do that? Well, maybe it has to do with the fact that when we are around us is the food, we want to go towards the food. So therefore we look at the food and we go towards it. So perhaps the evolution decided that the optimal path is to have the eyes in the front, focus to where the food is. And so that might be not unrelated to Aristotle's puzzle. Now, modern applications of symmetry breaking involves Higgs particle and the origins of mass. So in that context, that person is replaced instead of the origin as the height of the minimum, not at the minimum, but at the height as at the origin of the potential of a field called Higgs. And of course, the minimum of that potential will not be at that point, and it will be lower down. And the fact that you have to go to a lower down area for the lower potential will give you, turns out, explanation of the origin of mass, because it turns out that the mass of particles is proportional to how far away it is, the resting place of this Higgs field is, relative to the origin. And so it's amazing, it's almost poetic that the Higgs particle plays the same way as Aristotle's question about the person looking for food is. That circle that Aristotle was talking about could be viewed as a circle in the lower energy configuration for the Higgs field. So it's quite interesting that, you know, the human thought in trying to apply mathematics to the real world, you know, these ideas come again and again, and it's natural that it finds application somewhere, in this case, in the context of explaining the origin of mass. Now, mathematics is unreasonable. It's unreasonably powerful. So here I'll give you some examples of why math is so powerful, even simple math. You don't have to have a complicated math for it to be powerful. So here I'll give you some illustration of almost trivial math that's powerful. So consider the Earth on the equator. And suppose I take a belt and wrap it around the equator, and then I open the belt. So this is this white belt down here. And suppose I add 1 meter to the total length. In other words, just add 1 meter to this length, like this, and wrap it around the Earth. This time, it won't be snug. It will be a little bit, it will stand a little above the Earth. The question is, what's the height of this? How much above the Earth would it stand? So how many of you think it is high enough that you can pass a piece of paper under it? Say Y for yes and no for N for no. Can you pass a piece of paper from under this belt? Okay, so almost, well, it's hard to see the exact number, but it seems to me the majority are saying no. So some are saying yes. Okay, for those who are saying yes, how many of you think that you can pass a mice from under this rope? Okay, so again, some no, some yes. How many of you think that we can pass the skyscraper from under this rope? Okay, almost everybody says no. Yeah, it's kind of obvious, a skyscraper. Well, a few people said yes, surprisingly, but anyhow, it's almost obvious you cannot pass a skyscraper from this. But actually, let's see what happens. So first of all, if you call this extra height x, you can try to compute it using simple math, elementary grade math, really. So the original circumference is 2 pi r. If r is the original radius of the Earth, you add 1 meter to the total length of the circumference, and you want to write it as 2 pi times the new radius, which is r plus x. And so the 2 pi r's from both sides cancel out, and you get 2 pi x is 1, and x is 1 over 2 pi, which is about 16 centimeters. So this naive thing simply gives you the idea that it's actually about 16 centimeters, 0.16 meters, and therefore you should be able to pass a piece of paper and a mice from it. But actually, it turns out that if you could do something else, you could kind of push the belt all the way on one side, so it's snug on one side and it's not snug on the other one, and see whether you can make it push higher. In other words, if you pull on one end, you might think that this is, if the original length you have added is 1 meter, maybe you can pull it half a meter up just by pulling on one side, not all uniformly around the equator, but non-uniformly. What about that? Well, it turns out that if you do that, this turns out to be 121 meters. Now, this is surprising. And it's hard to believe it's true, but I encourage you to do the math and check it. Using simple calculus, you can check it, that the length that it gives you is 121 meters, despite the fact you only added 1 meter to the total length of the rope. So you get some unintuitive results from some simple operations like this. So now I give an example of the power of continuity. So in physics, one of the basic features of physics is the fact that the laws of physics involve equations and they are continuous. So there's continuity is built into the physical laws. But continuity is also a powerful principle in mathematics. So let me give an example of how this works. Again, by illustrating in a simple way, let's go back again to our equator, and we consider the equator, and we ask what is the we consider the temperature on the points on the equator, and ask what happens whether or not the temperature as it varies across the equator, whether the temperatures are the same or different as we go around the equator. And in particular ask, is it possible that 2 points oppositely situated relative to the center of the Earth on the equator have the same temperature? Well, of course it could, why not? But the question is, are there always 2 points located diagonally opposite relative to the center of the Earth which have exactly the same temperature? Of course, the question is not that whether there are 2 points which have the same temperature all the time, but whether there are at any time 2 points which you can find 2 points such that they have the same temperature. How many of you think the answer is yes? How many say no? Okay, so majority of you say yes. And indeed, the answer is yes. The way to see it is, again, using simple idea of continuity, because we're assuming the temperature varies continuously. If you continue calling the angles opposite to each other by plus and minus, then let's consider the difference of the temperature from one side to the other. Let's define a function, which is the temperature of opposite antipodal points. And in this case, the difference of the temperatures, if it is 0, you're done, because that would say that if this f at any value was 0, you'd find that the temperatures are equal. And that's what you want to show. Suppose it's not 0. You choose a point theta. And suppose you choose an angle. At that value of the angle, you compute the difference of temperature from one to the other, and it's not equal. Okay? Now, if you go to the opposite point, if you move from theta to minus theta, then you're measuring the same temperature difference, but now in the opposite order, and therefore the sign flips. So if you go from one point to another point, which is opposite to it, that function takes its value from whatever value it had to a minus itself. So if it was positive, it will go to negative. If it was negative, it will go to positive. But temperature is a continuous function of angles. So if you go from one negative to a positive value, let's say, you will have to cross 0 somewhere, and simple continuity implies this. And therefore, that means that wherever it crosses it, at that point, the temperatures on the two sides were equal. And this is an illustration of the continuity, the power of continuity. And I will leave it as an exercise to those of you who are inclined to use similar continuity arguments to show that not only temperatures at 2 points on the equator are the same, at every moment there are 2 points which have equal temperature, but on the Earth, there are always at least 2 points for which the temperature and pressure are equal. So two things are equal, and that I will leave it as an exercise. So the next thing I want to talk about is gravitational lensing. So this is another example, a powerful example of continuity. Einstein's theory describes the fact that the geometry of space get bent by having matter around, and in particular, the light ray will follow paths which won't be, even though they are geodesics, but they will not be straight anymore because the fabric of space-time is kind of curved. So what happens is that if we are here on the Earth, and if you're looking at the faraway galaxy, it could be that more than one path of the light ray gets to us from the same galaxy. So if we are on the Earth here and we are looking at that galaxy, we might be getting two different directions which are actually the same galaxy. So in other words, we would get multiple images of the same object. This is called gravitational lensing. So for example, in this picture, you may not know, but actually there are a lot of repeated objects in this picture. You might think there are all these different objects, but it turns out that they are repeated, many of them. So indeed here, the blue circles correspond to the same quasar, and the orange ones correspond to the same galaxy. So in other words, we have 3 galaxies here of the same type, of the same galaxy, not the same type, same galaxy, and 5 blue quasars, which are the same quasar. They just appear to be different because they come from different directions. So the light ray has come from different paths to us. It's quite remarkable. Notice that the number of images is odd here. You have 5 images of the single quasar and 3 images of the galaxy. It turns out, that's a fact, that the number of gravitational images that you get, if none of the images is blocked, is always an odd number. And just less than half of them are inverted images. So in other words, if you have, for example, 3 images, you get 2 of them upright and 1 of them inverted. And if you have 5 images of a given object, you will have 3 of them upright and 2 of them inverted. Now, you might think this is an amazingly difficult fact to establish. It has to do with, Einstein's theory and solving these complicated equations. How could you possibly show such a statement? And it turns out, again, it's a consequence of simple arguments having to do with continuity. And so this application of continuity is a bit more sophisticated, but not much more than the original one. So I will try to illustrate it. It will involve a little more math, but at least it will give you a feeling of why there should be such a simple picture. So here we have a map. So we have a light rays which get to us from a given object. Here I'm denoting that galaxy or star or whatnot in terms of a red circle here, red disk here, and its light ray gets to us by some paths to the Earth. Now let's do the following. Let's consider concentric spheres whose center is this star or galaxy that we are trying to see from the Earth. And let's take one sphere very close to us, passing through where we are on the Earth. Now, suppose there's no matter between us, just empty space. There's the star, or there's this galaxy and us, and nothing in between us. What will happen? Well, what will happen is that every light ray goes in a straight path. These yellow lines denote the light rays that are emanating from the star, and they all go straight line. Now, as you see, every point, the light ray which crosses a sphere near the star will hit the same point in the sphere which is farther away where we are. In other words, the light rays themselves give you a mapping of a sphere surrounding the star to the bigger sphere, which is where we are. So I denote these two spheres by S2 with the red and the Earth sign, saying one of them is a sphere near the star, and the other one is a sphere passing by where we are. So the light rays provide a map from one sphere to another. This map is a trivial map in this case because it takes every point on the sphere to the same point on the other sphere, just because that's the way the light ray goes when there's no matter in between. Now we can define the notion of what is called the degree of a map. And the degree of a map is the net number of points which get mapped to a particular point. So if you take our Earth as one point on this bigger sphere and ask how many points on the small sphere get mapped to that point, in this case, it's just one. That's exactly the number of images that you're going to see, namely the number of points that get mapped to that point is called the degree of the map. Actually, not quite. It's more precisely the degree of a map is the net number of pre-images of a given point, but counted with a plus or a minus sign. So you count it with a plus or minus sign, depending on whether the map is inverted or not. And it turns out that degree of a map is something that does not change, is a property, as a continuous, and it does not change under any process. Topologically, you cannot change it if you have a continuous map. So as I said, the degree of the map, when it was no matter between them, was 1. And when you have matter in between, the degree should still be 1. So let's illustrate this by the following animation. So here, this is the Earth, and there is the light ray will go through the straight path, and it gets to us, as we illustrated, from the center of the sphere where the star is located. However, let's see what happens if we put some more matter. Putting some more matter twists this map and makes the map look more complicated. Looks like it has some complications around, similar as if the sphere around the star was kind of twisted. And if you take this and then look at the map now, if the Earth is where it is now in this image, then you just see one light ray hitting us from this path, which is that one image we set. But if Earth was located somewhere else, if it was moving around somewhere else, over here, for example, you see again one. But if it moves somewhere else, now you see that there are 3 of them. You see there are 3 blue things that are being crossed by that light ray. So there are 3 different paths it could take in this map. And then here it would pass through 5 of them. And you see the plus or minus signs which are denoted here. Plus or minus denotes, as you traverse around the circle, which orientation you get it. In one case, you go forward, and the other one, you go backwards. So back and forth corresponds to orientation preserving or reversing. And it turns out here you get 3 orientation preserving maps and 2 orientation reversal maps. So this is a kind of illustration. It's a bit more sophisticated application of continuity. Now, here I'll give you a power of mathematical abstraction of why abstractness is a good idea sometimes to do in math. So I illustrated by the following puzzle. So this puzzle involves ants. The ants are moving on a plane with a constant velocity. Each ant has a constant velocity, but they point in different directions and their speed may not be equal, but each one has its own speed and maintains that speed, and it goes in that direction on the plane. And what we are told, so there are 4 ants, and what we are told is that each pairs of ants actually pass through the same point at the same time. All the ants pass through the same point at the same time. So in other words, they all collide and they pass through each other at the same time, except for possibly 2 ants, for which we do not know if they do cross or not. So suppose all the ants collide, except 2 of them, ants 1 and ant 2, these purple and this orange ant, will they necessarily have to collide or not? How many of you think, yes, they will have to collide, say Y, and how many think, no, they don't necessarily have to collide, say N, no? Okay, so we are getting by and large yes and no answers. I would say maybe slightly more than average would say are saying yes, but maybe no, maybe it's like half-half. At any rate, what's the point of this puzzle? Well, you can sit down and do calculation and check it, but it turns out the easiest way to solve this puzzle is by going to higher dimensional space-time. In other words, here we are thinking about the space as 2-dimensional, but it's better to add one direction, which is time, to this axis. So if you add the axis of time, so you have 2-dimensional space, which is this plane, and 1-dimensional time, you have a 3-dimensional space. And these ants, which are going straight and the continuous speed, constant speed on the plane, in the context of the space-time, their line corresponds to a line that they traverse. And the line that they traverse is going to be a straight line in this 3-dimensional geometry. So 2+-dimensional geometry, which is going to be straight line. If 2 ants pass through the same point at the same time, it means that these lines that they have in space-time, they cross. So therefore, we are saying out of these 4 ants, pairs of these lines will actually cross. So out of 4 ants, pairwise, they cross. And so each time these lines cross, they form a plane. So if 2 ants' paths cross, they form a plane because they are crossing, their lines cross. If a 3rd ant crosses those 2 ants, it should lie on the same plane because they will form, each of the pairs will form a plane, and therefore the 3 will be forming a plane. And so let's see if we can use it to happen to these other ants. So, let's take this 3-dimensional perspective. We raise the time. And these ants, as they're going in constant velocity in space, they're going higher in time. So therefore, they form a plane. And so you see that ants are forming these kind of planes that have to cross. In other words, the ants that we were asking, the 1, 2 ant, the purple and the 1 and 2, what I call them, have to cross because of the following fact. You see the 2, 3, 4, this yellow triangle is formed because the 2, 3, 4 ants cross each other. So that forms one plane. And the other one, the 1, 3, 4, also cross, they form another plane. And therefore, since there's not more than one plane passing through these two lines, therefore these yellow and the green planes are the same, and therefore the ants 1 and 2 are on the same plane, and therefore they have to cross. Since their directions are not parallel, as we assume they're going different directions, they will have to cross. So again, abstracting the notion of higher dimensional space-time was useful. In string theory, extra dimensions buy a lot of things for us, and this abstraction is an example of how sometimes thinking abstractly about the problem solves the problem much more elegantly. Now I come here to the notion of duality. One of the amazing things that has been discovered in the context of string theory is duality. Duality refers to the following physical phenomena, that 2 seemingly different systems can nevertheless be identical. Identical despite the appearance. In other words, the appearance might fool us to think they are very different, but actually they are the same. And a beautiful artistic depiction of this is through this drawing of Escher, which shows, in this drawing, you would think that different corners of this drawing are different things going on, So in one place, you think that you're dealing with the day on the upper left corner. On the upper right corner, you're seeing it's night. On the left corner, you are seeing there's a white sky. And the right corner, you see that that white sky has actually transformed or morphed to becoming a white bird and so forth. So that's from left to right, and from up to down, you see that the black birds and the white birds are becoming black and white fields and so forth. So different things are going on. And the duality in this context is a gradual transformation from one side to the other, and they all fit together and they're all consistent. But you might be thinking that one side is describing it incorrectly. If you are living on the left side of this, you would say, oh, of course it's day, and of course there are black birds. And if somebody said, no, those black birds are actually black sky, and the white sky is what you're talking is the white bird, you might say, no, that's absolutely wrong. But gradually, as you go from left to right, that becomes correct. So duality is kind of changes the perspective depending on exactly which region in parameter space you are. In this context, where in this field you're located will give you a completely different perception of what is going on. So here's the next puzzle related to duality. So we have a meter stick, 1 meter, and we have ants on these meter stick. Again, I love the ants, so ants are my favorite descriptions of the puzzles. So ants are moving on this meter stick. The ants are going either from left to right or right to left with the same speed. Unlike the other problem, their ants are going all with the same speed, let's say with 1 centimeter per second. The meter stick 100 centimeters, and each ant is going 1 centimeter per second. Now, the ants are either going right or left, but there's only so much room in the meter stick, so they come and collide. And each time they collide, they reverse direction and go backwards until they meet the other ant coming the other way, and then they again collide and then reverse direction and go. If they were going from left to right, they go from right to left after the collision, and vice versa. So that's what they do. But the meter stick is only 1 meter, and it's at the end there's no edge. So as the ants get to the edge of these, as the ants get to the edge of the screen, it is they fall off the screen. So here I'm illustrating that. You see, for example, these ants are moving and they're colliding back and forth, and if they go to the edge of the meter stick, they fall off. So suppose we have 20 ants. 20 ants, the meter stick is 100 centimeter, and you want to place the ants, and you instruct the ants whether they should go left or right. You choose which direction each ant goes. You can put them near the center or far away, whatever you want. You choose 20 ants. You put them in such a way to make the ants last the longer. The last ant falls off the meter stick later. The longer, how do you maximize the time the last ant falls off the meter stick? And can you put your answers on the chat? How long do you think this maximum time could be? Infinite, finite, what numbers? Just put numbers, please. Guess how much is the total time? Just numbers. Is it 1 second, 50 seconds, 100 seconds, 200 seconds, infinity? Can we make them long and last infinitely long? Okay, so some people have said 100 seconds. Some people said, what is the speed again? So the speeds are so let me say what the speed is again. The speed is 1 centimeter per second. The meter stick is 100 centimeters, and you have 20 ants. Okay. Very good. So some of you suggested 100, some of you an hour, some of you shorter. It turns out the answer is 100 seconds. And to see this, it is good to use duality. This is a relation to duality transformations. You see, I told you that the ants are, when they collide, they reverse direction. But suppose I colored the ants black, and you're looking from far away. Would you know whether the ants after collision reverse orientation direction or not? You wouldn't, because just look at it. If you had a situation like this, and if you look at the ants, whether they collide and go backwards or not, it looks like as if they're crossing and going through each other. There's no difference as whether they're going through each other or colliding and reversing direction. In other words, there's a duality transformation which reverses the identity of the ant after they collide, and it does not change the answer for this question of how long it takes. And therefore, the best you can do is you don't care about what you do with the 20 ants, as long as you put one ant at one edge of the meter stick and direct it to go to the other direction, it will take 100 seconds. Because it's 100 centimeters and 1 centimeter per second, leads to 100 seconds. So again, this is a simple idea. Again, the duality gives you a natural resolution of this puzzle. Now, finally, and this is my most fun puzzle, is the following, is to understand how we think about science. What is the scientific methodology? To illustrate how we do science, and this is very useful to explain to others that what is the basic steps in learning and doing science. Namely, we have examples, which we call experiments. We formulate general principles based on those examples. We try to explain and motivate these general principles and come up with arguments why it works and how it works. And of course, we continue checking the experiments and making sure that we got everything right. This is the basic paradigm of how we continue doing science and reformulating and learning more and more. So let me illustrate this with a puzzle. Here we have a circle, if you wish, a disk. And what we're going to do is we're just going to choose random points on the circle. First, we start with 2 random points on the circle. And we connect these points by a line. And we ask the following question. How many regions does this line divide the disk into? Well, it's not hard to see that in this case, we have 2 regions. So in other words, if you have 2 points on the boundary of the disk, you get 2 regions. Now, suppose I continue this process and adding 1 more point. And again, add every point to every other point. And ask, how many regions do I get now? Well, exactly, we get 4. So 3 points, we get 4 regions. Okay, what about if we continue this? Now, we are going to choose random points. So generic points on the circle, not special points. We don't fine tune where we choose it, we choose random points. So let's choose another random point, the 4th point. And then we connect every point to every other point. And then we ask again, how many regions do we get? We get 8 regions. Okay, I think you're getting a pattern here, I hope. So now we get 8 regions in this simple way, but now we can continue this after 4 points getting 8 regions. You see 2 points give you 2 regions, 3 points give you 4 regions, 4 points give you 8 regions. And so I will ask you, if I add 1 more point, 5 points, how many regions do I get? Can you type your answers? Okay, some people put 16, 20. Okay, so people answered, majority answered correctly, 16. Why is that? Well, it's because you think about why is it happening like this? Well, the answer is kind of clear, because each point is, when you connect it with a line, you get regions, and you get a formula like 2 to the n minus 1. Each point is a number of points, you're getting doubled. And the reason it's doubled is that you have something on the left and something on the right. So you have an explanation, you have a formula, it works beautifully. So if we have 6 points, how many should we get? Everybody? Okay, so let's see. So almost everybody says 32, but some people don't like 32 for some reason. Let's see, why are they saying so? Well, actually, if you just count it, you find with 6 points, you get not 32, but 31 regions. Okay, what happened? Well, you might think that I chose the points in a funny way. No, I did not. It turns out this is generic points I've chosen. I've chosen 6 generic points, and you get 31 regions, not 32. So indeed, what happened was that our theory was wrong. Our explanations was also wrong. And the actual formula turns out to be this. It's 1 plus n choose 2 plus n choose 4, and it gives you 31 and not 32. And if you put 7 points, you get 57 regions and not 64. So this is an example where we come up with experiments, we come up with examples, we do have some kind of an explanation. It sounds reasonable, and then upon further scrutiny, we find it doesn't quite work in experiments, and then we refine our theory and we come up with the correct formula. So this is again and again happens in physics and in all science. So I hope I have conveyed the power of simple mathematical ideas in the context of physics. Even the most advanced ideas in string theory have simple mathematical underpinning, just like the puzzles we have discussed today. So thanks for listening to my talk. So I'm happy to take questions if that format is possible. Let me stop my sharing my screen, perhaps.
Great. Thank you so much, Professor Vafa, for that beautiful experience that we had. I think this was a first for our audience. So maybe we could, the organizers, the co-hosts could unmute everybody and we can have a round of applause for Professor Vafa.
Thank you. It was a pleasure.
So usually what we been doing in the past is the attendees, they type in their queries and then we take them up towards the end of the talk. This time it was kind of the reverse. It was you asking them the questions, so which is a good twist. And so I don't know, maybe since if somebody has some quick questions, they could probably type in those questions real quick. Maybe we can give them, if you, with your permission, maybe give them a minute or so. Will that be okay?
Sure.
Professor?
Sure.
So maybe, yeah. Okay. So if folks have some queries, you're requested to type them in the chat, and we'll try to take some of them up.
One person is asking if changing the positions of the 6 points will make a difference. Yes, if you chose non-generic points, the answer will change. So I've taken 6 generic points, and for the generic points, the answer would not change. Thanks for your kind comments, by the way, on the chat. I welcome questions. How should interested undergrads approach learning string theory? I think it, as in any science, you have to build up to the subject. So if one is interested in string theory or more generally, more broadly, high energy physics, you will be starting by taking physics courses, you know, the basic steps, classical mechanics, electromagnetism. So you concentrate in physics and quantum mechanics and then quantum field theory, more math at the same time. So learning both math and physics, and at some point you'll get to study general relativity and then string theory. So there's a path to it. It's just a lot of studying has to be done to get to there. It's not going to be, unfortunately, just one course. So if string theory is correct, we have unified field theory by now? Should we look in different direction? String theory being correct does not have to be verified today. That's the question that we don't know when it will be verified. That's the question. We don't have experimental verification of string theory today. Just give you an example, Maxwell, when he wrote down his equations, he predicted that there is light, electromagnetic wave moving, but he couldn't demonstrate that the light actually was electromagnetic waves. So it took a while for things to settle down. String theory, I think, would have due to this complexity and the fact that the size of the strings are tiny, it have much later time before we can actually get to the point where we can experiment it. But already by the things that we have learned from string theory, it gives a lot of confidence that there is some deep structure there, and that many of us physicists believe it's the correct description, and that's why we are pursuing it. It has impacted many different areas of high energy physics and theoretical physics. More broadly, even condensed matter physics has been impacted by many of the ideas on string theory. They asked some questions is, can we have vibrating surfaces like vibrating strings? And that actually turns out to be a very good question. It turns out that we have learned that it's not just vibrating strings, that strings are just one example of these extended objects, that string theory actually does allow and does have extended objects like vibrating surfaces and even higher dimensional objects more than 2 dimensions. So indeed, that's correct. Since there's rotational symmetry, how do we define up, down, and right image? In the image, when I said it's inverted, what I meant was that you have, rotation is, if you rotate an image, I wouldn't call it right side up, I meant more precisely reflected. Right side up means reflection. So if you rotate it continuously, that doesn't do anything. But reflection, like in a mirror, you know what's left or right. So that's what I mean by right side up means, or left-right exchange. Are there any alternative to string theory? I would say that there are some people who would like to suggest alternative, but to be fair, I think none of them are at the level that string theory hasn't developed. So I would say currently, no, there is no alternative, no real alternative to string theory. Can string theory explain whether black holes are consistent with quantum mechanics or not? Yes, indeed, they seem to be, there are good arguments from within string theory which suggest why the black holes are consistent with quantum mechanics. And that's one of the areas that string theory has made some progress, even though we have still yet to understand many of the puzzles of black holes. So I don't claim that we have completely understood black holes, but well, it seems like in the context of string theory, we have some solid arguments why quantum mechanics is consistent with black holes. And in particular, the unitary evolution of black holes does take place. Yes, and the example of Einstein's gravitational waves being discovered after 100 years is a good example that you have to sometimes wait to see a verification of a theory. So how can one develop a physical intuition on the Ramanujan sum converging at -112, which is the key math formula used in deriving the equal 26 bosonic string? Well, physical intuition in some things like that is hard to come up with. And so I wouldn't say that I have an intuition, for example, to this. So we can try to have a better explanations, but sometimes the physical intuition comes up by trying to do an explanation by the analogies. So for example, for the summation of integers being -112, one way of doing it is to define not the summation of integers, but integers plus a fraction x. And if you study that fraction and you study what happens to that fraction at x equals to 1/2, and put them together and do a few manipulations like that, you can actually come up with the summation of integers being -112. Now, you may not call this a physical intuition, and it's not, but it actually gives you a little bit of more of a feeling of why it works. It's just like saying if you take a summation of 1 plus 2 plus 2 squared plus 2 cubed, etc., the geometric sum with the 2's there, you would ask, this sums to -1 despite the appearance that's divergent, and that's just because you can analytically sum it up to get 1 plus x squared, etc., to becoming 1/1 minus x, and if x is 2, it gives you -1. So you can geometrically resum it, and so you can have some explanations along those lines, similarly to this sum. Is this the same with the conservation of angular momentum? Since we have never seen a violation, we believe it's true. Well, we could be, for example, the angular momentum, we have violations observed, and we have kind of an explanation, theoretical explanation of it. So those fit together, and if physics points to a different direction, of course we will study it and we understand it. But right now that seems to be the principle, similar to that circle principle, the circle puzzle that I gave. Somebody is asking, what about loop quantum gravity? I said there's no other quantum gravity theory. I would say they are not at the same level as string theory. There are some ideas in the context of what people call loop quantum gravity. I wouldn't say they're at the same level of development of string theory. For example, the precise measurement of the entropy of the black hole in the context of string theory has not been done in those theories. Is space-time emergent from quantum mechanics? We think space-time should be emergent in the context of string theory, and quantum mechanics should be emergent from space-time as well. There's a duality, actually. So it's two-way street somehow. Again, the detail of how time emerges, we don't understand very well. We have, in cases, understood how space can emerge, but understanding that the emergence of time is still not complete. In lensing, should not the number of images seen depend on the type of object causing the lensing? No, the number of images is always odd. Of course, there are some exceptions in the following sense. You can have, for example, a circle and the middle of an object such that the circle, you get a ring of an image. So you can have some exceptional cases. So I'm talking about generic cases. And of course, you can block a light, and I'm not doing that. If you don't do any of those, you always get an odd number of images. What string theory ideas had impact condensed matter? Holography is one area. Other areas have to do with topological features of string theory that has impacts of string with condensed matter as well. How do I come up with these puzzles? Actually, I came up almost with none of these puzzles. These are not my puzzles, so let me make that clear. These puzzles are, many of them are known, and I got to hear them from here and there. I do not know, unfortunately, the origin of many of these puzzles, otherwise I would have mentioned. And some of them I maybe modified a little bit here and there, but they are not the puzzles due to me. Perhaps the main thing that isn't perhaps novel is the connection with physics. How do we learn from these simple puzzles, pieces of physics? Some of these puzzles were refined by my students in the class and so forth. What does it mean? It's not possible to locate a degree of the region of phase space within a volume smaller than the Planck constant. So there's a notion of the fact that we cannot get any distance smaller than the Planck distance described in the context of physics. That's one of the facts of quantum gravity. Though I do not think it was directly related to the talk, but at least that's the fact. What is mirror symmetry? Mirror symmetry is a statement that it's another example of duality. So I talked about duality, two things which look very different could be the same. Mirror symmetry is an example of it. You have a space which has a different number of handles and holes, another space which is completely different. They behave exactly the same way. And a simple example of it is that if you take a box of size L, and if you take this box to be smaller and smaller, if you take L to be going to be very, very small, it turns out if you pass the string scale, it becomes very small, it's equivalent to a bigger box. So there's a symmetry, inversion symmetry. L length going to 1 over length in string units is a symmetry, and that's a simple example of mirror symmetry. Is the thickness of string 0? Ideally, string thickness is 0 in perturbation theory, but fluctuations of string would give you an effective width to a string. So in some sense, you develop a width. In the gravitational lensing problem, I have to apologize by the picture I drew, because the picture I drew does not do justice to the actual physics. I was just trying to illustrate the fact that the degree of map should be constant by a visual perception. That was not the description of that was not faithful to the physics description, but was trying to illustrate why the degree of a map is constant. So I apologize for that. Is it possible that time does not feature in a grand unified theory? It is possible that time emerges in some form. We expect that to be the case. Do we expect the time to be quasi-cyclical? Maybe not quasi-cyclical, but the universe could be quasi-cyclical in the sense that when this universe gets smaller and smaller, it could be equivalent to getting bigger in these kind of inversion symmetries, for example. Time travel. Time travel is possible to the future, but not to the past. In fact, time travel to the future is already demonstrated by Einstein's theory, because if you go fast, the time slows down. So in principle, you can travel to the future. But time travel to the past is not possible. It's inconsistent with logic. Do we have models in which graviton interact with Higgs particle? Yes. In string theory, we do have models where you both have a Higgs particle and a graviton, and they're consistent together. What is the concept? Singularities in string theory, spatial singularities in string theory have been understood better than time-like singularities like the ones in black hole. So some singularities we have understood how they work in string theory, but not all. Thank you for the sessions. I think I have answered all the questions I could see in chat. It was a wonderful experience to be able to communicate all this with this very interested audience, and it was a very great pleasure for me to share this talk with you. By the way, for those interested, this puzzle to unravel the universe is available in the India's Amazon, but that's all I want to add.
We are so grateful. Really appreciate your patience with all the queries. I mean, this was so cool. I mean, it's like it was you and the audience. I mean, we literally had no role to play, and that was just beautiful. Thank you so much. We really
thank you for organizing it. You had a lot of role, and also the astronomy club, astronomy physics club was. Did handle it amazingly, and I'm grateful to all of you guys.
Thank you so much, Professor Vafa. So I think before we end, I just wanted to make a reminder. It's already been posted on the chat. Everybody is requested to kindly fill in the feedback form, the link of which is already visible. And we are so grateful once again, Professor Vafa, for your time and patience. And thank you. Thank you. Have a great day.
Thank you very much. It was a pleasure meeting everybody here.
Okay.
Hopefully better times. Keep safe.
Okay. Thank you so much.
Thank you.
Bye.